Swayam Prabha. Digital India. Educated India.
Good morning and welcome to this the 10th lecture of the course Stochastic Hydrology. If you recall, in the last lecture we covered the methods of data generation, where we dealt with generation of data when the distributions are known. For example, we discussed how to generate data from a normal distribution, exponential distribution, gamma distribution and so on. So, essentially what we do there is that given the CDF, we assign a uniformly distributed random number and equate it to the analytical expression of CDF and solve for y. For example, capital F of y is equal to RU, random number uniformly distributed random number in the interval 0 and 1, and then solve for y. In cases where explicit solution for y is not possible, then we have other methods. For example, in the normal distribution case, we have the standard normal deviates, tabulated values of those. We use those tabulated values and then solve for y, and these are the generated values. Then we went on to discuss the time series concepts. We have just introduced the concepts of time series. If you recall, a series of observations on a random variable across time constitutes a time series. For example, you have stream flow data over the last about 50 years. Stream flow observations made every month for the last about 50 years, and this series of observations constitutes a time series. So, we will continue the discussion today on time series analysis and then introduce also some data forecasting techniques using the methods of time series analysis. So, if you recall, in the last class we first defined what is a time series. As I just mentioned, sequence of values of a random variable collected over time. Although I must mention that although we keep on emphasizing collection over time, it can also be a space. For example, we may have rainfall sequences across a space. Now, the techniques that we are discussing are also applicable in some cases when we have large observations across space. Now, the time elements over which we are making the time intervals over which we are making the observations can be discrete or continuous, and they lead us to discrete time series and continuous time series. We also introduced the concepts of the realization and an ensemble. Realization is a single time series, that is, if we have one time series, one set of observations across the time, that is called as a realization. So, this is a realization of the time series. For example, we may have sequence of stream flows observed between 1970 and 2000, that constitutes one realization. Like that, we may have several such realizations. For example, stream flows between 1940 to 1970, 1970 to 1990, 1990 to 2005, etc. Like this, you have several such realizations possible. The collection of all such available realizations is called as an ensemble. Generally, in the case of hydrology, we do not have large number of realizations. In fact, if we have one realization with a long series of data, then if necessary, where in cases where necessary, we split the time series into several realizations. For example, if we have data from 1970 to 2000, we may take data from 1970 to 1990 for example, as one realization, 1990 to 2000 as another realization, and so on. In general, in hydrology we may be dealing with a single realization. The hydrologic time series, in fact, in general any time series may consist of a deterministic component and a random component. For example, you may have a long term mean of a hydrologic variable around which there are random fluctuations. So, we would like to model the time series by capturing this deterministic component and by modeling the random components. So, in general we write the time series x t as consisting of a deterministic component d t and a random component epsilon t. This is what we discussed in the last class, and we have also seen that a time series may in general consist of a purely stochastic component. That means, there is no deterministic component at all, the values are all randomly fluctuating like this, in which at any time t, if you take the observations between time t and time t plus 1 have no relationship with among themselves. On the other hand, you may have a deterministic component which is a trend, let us say in this particular case an increasing trend. So, around an increasing trend the values are randomly fluctuating. If you look at the global average temperatures over the last, let us say 50 years or some such thing, that will have an increasing trend and the values are randomly fluctuating around that. So, you have the stochastic component as well as a deterministic component, which in this case is the trend. Then you may have a periodic component, the values are randomly fluctuating. So, you have a stochastic component around a periodic component. If you look at, let us say, monthly stream flows at a particular location in monsoon regions like ours, then you may have such periodic components prominent in that. Then you may also have cases where there is a jump. As I mentioned in the last lecture, these jumps may occur because of sudden large scale changes occurring in the catchment. Let us say you are talking about stream flows in a basin, and a large scale either deforestation occurs or large scale fire occurs or a huge earthquake occurs in that, which in a short period disturbs the hydrologic balance. Then the hydrology starts operating at a different level altogether. This may be either a jump or it may be a drop. What was operating at this level on an average starts operating at certain other level on an average. So, you have a stochastic component and a jump component in this. So, once we capture the deterministic components, we write x t is equal to that deterministic component at time period t and a random component at time period t. This deterministic component itself may be a combination of the long term mean around which fluctuations are occurring, a trend, a periodicity and a jump. Now, the discrete time scale observations in hydrology arise mainly when we are talking about, let us say, monthly stream flows. Although the observations may be done every day, for the analysis we may consider the aggregated values of the stream flows over a month, and therefore, we may be talking about monthly stream flow, average monthly stream flow, or annual peak discharge. That means, every year we have one discharge value, which is chosen as the maximum discharge of all the discharges that have occurred over that year. Daily rainfall, we measure the rainfall at, let us say, 8 a.m. in the morning today, and next again tomorrow at 8 a.m. we measure the rainfall, and that such sequence of observations constitute a discrete time scale time series. On the other hand, you may also have continuous time scale time series, where data is recorded continuously with time. For example, in turbulence studies or in experiments where we are measuring pressures. So, these measurements are across continuous times. In most cases where we are dealing with hydrologic time series, we will be dealing with discrete time scales, because we have observations at discrete times, that is the first thing, and also the analysis is required at discrete time steps. For example, we will be interested in forecasting for the next month or next 10-day period, next day, and so on. So, we will be dealing with discrete time series. The PDF of x t, now remember x t becomes a random variable. So, x t has its own PDF, x t plus 1 has its own PDF, x t plus 2 has its own PDF, etcetera. So, across time you are having collection of random variables, and the process behaves in a certain probabilistic way at time period t, which may be different from its behavior at time period t plus let us say tau, and therefore, the PDF is now denoted as f of x comma t. Now, f of x t describes the probabilistic behavior of x t at specified time t. If we have the PDFs of f of x comma t, that is PDF f of x comma t, the same across time period. As time changes, the PDF does not change. Then the time series is said to be stationary. That is, if the PDF at f, the PDF f of x t is equal to f of x t plus tau for all time t, that means we are considering a lag of tau, and then if the PDF remains the same across the time for all time period t, then the process is said to be strictly stationary. So, for stationarity of time series, PDF of x t is the same as PDF of x t plus tau for all t, where tau is the time lag that we are considering between the two random variables. So, this picture makes it clear. You have several realizations. This is realization 1, realization 2, etcetera. So, you have m realizations, and this collection of m realizations is the ensemble. So, you can talk about properties across time or properties across realizations. So, when you are looking at one time series and then you are looking at properties across time, then we have time properties of a given realization. For example, you may look at the time average of a realization, which is you are taking the average across time, and therefore, you can write this as for the first realization, for realization number 1, you can write x 1 bar as sum of all the observations across time for the same realization divided by the number of observations. So, that is what you are writing formally here, that is x j t for the realization 1 across all j is equal to 1 to n, you have n number of observations. So, essentially you are taking the average across time for this realization. These are called as time properties, or in this particular case it is called as the time average for a realization. Similarly, you can look across the realizations at a given specified time t 1, you can take averages across realizations, in which case you talk about ensemble average at time t. So, that will be given by x bar t is equal to t is equal to 1 to 1 m summation, that is you are summing x 1 t at t is equal to t 1, x 2 t at t is equal to t 1 and x m t and so on, and divided by number of realizations. So, you are essentially taking the average across realizations. This is called as an ensemble average. There is a concept of ergodicity, where the time average properties will be the same as the ensemble average properties. In such a case, we call the process to be an ergodic process. So, for stationarity, as I said, the process is strictly stationary if the PDFs across time remain the same. That means, if you consider two time steps, tau time steps apart, that is t and t plus tau, the PDF at t and PDF at t plus tau remain the same for all t. So, even if you shift by tau across time scale, the PDFs remain the same, then it is called as strict stationary time series, a time series which is strictly stationary. However, in most applications we may not need strict stationarity. We then define a weak stationarity. For example, if the PDF is not the same, but if the means across time are the same, then we call the time series stationary in mean. So, in general, if we have a time series, if all the moments up to order f are the same for time t and t plus tau for all t, then the time series is weakly stationary of order k. For example, k is equal to 1, it means that the moment up to order 1 is the same across time. The first moment is mean. So, if you have x t is equal to x t plus x bar t is equal to x bar t plus tau for all t, then it is stationary in mean or it is a first order stationarity. Similarly, for k is equal to 2, we will be dealing with moments up to the order of 2, which means the mean should be the same and the covariance should be the same. So, k is equal to 2 refers to stationarity in mean and covariance both together. It can be shown that if it is if a process is stationary in covariance, then the variance also remains the same. So, it is stationarity in mean and covariance also indicates that the process is stationary with respect to variance, which means the variance is also constant across time. Remember here, when we say k is equal to 2, it must be both stationary in mean as well as in covariance. If the process is stationary in covariance, but not stationary in mean, then it is not weakly stationary of second order. Again, for a strictly stationary time series, you must have the PDFs to be the same, PDF f of x 1, x 2, etcetera must be the same across time. Then we come to the concept of autocovariance. So, from now onwards we will be dealing with stationary time series. So, unless otherwise specified, we are always assuming stationarity with respect to mean and variance. So, autocovariance, recall that when we defined covariance, we defined it with respect to two variables x and y, covariance between x and y. Now, we are dealing with a single random variable which is let us say stream flow measured at different time steps, or the properties of the random variable at different time steps. X t is a different random variable and x t plus k is a different random variable. So, we define the covariance between x t and x t plus k as expected value of x t minus mu, x t plus k minus mu. Recall that covariance between x and y, covariance of x comma y was expected value of x minus mu x into x y minus mu y. So, we are simply replacing x by x t and y by x t plus k. So, from this definition then, what happens when k is equal to 0? We are talking about covariance of x t with x t itself, and that turns out to be in this particular case gamma naught is equal to sigma x square, which is the variance. Then we define the autocorrelation. What did we define the correlation as? Correlation coefficient as covariance between x and y divided by sigma x sigma y. that is a normalized covariance. So, much the same way we define the autocorrelation as covariance between x t and x t plus k divided by sigma x t and sigma x t plus k. And for a series which is stationary in mean and variance, this comes out to be, because sigma x t is the same as sigma x t plus k, and therefore, this we write it as gamma k by gamma naught, because sigma x square, which is a variance, is nothing but gamma naught, as you can see here. Also, when k is equal to 0, this becomes gamma naught by gamma naught, therefore, rho naught will be equal to 1. So, the lag 0 autocorrelation is 1. The plot of rho k versus k, rho k is as defined by this. So, we can talk about the correlation with respect to various lags k. This k is called as the time lag or simply the lag. So, rho k in some sense gives a measure of dependence of the variable x t plus k on the variable x t. So, it indicates a measure of dependence. So, if you plot rho k versus k, this indicates, this is variously called as correlogram or autocorrelation function. This actually indicates the memory of the process. That means, how far into the time it remembers. For example, x t plus k depends on x t. Let us say k is equal to 12 in the case of monthly stream flows. Let us say you are talking about the flow during the June of a particular year depending on the flow during the June of the previous year. And if the time series consists of monthly stream flows, then we are talking about a lag of 12 months. Then k is equal to 12, and then we may have associated rho k value here. K is equal to 24. The dependence of June month's flow on June month's flow of 2 years before, that is 24 months before, and so on. So, as k increases, you may have smaller and smaller rho k values. On the other hand, you may also have a periodic oscillation of rho k value. So, essentially rho k or the autocorrelation function indicates the memory of the process, how far into the time is it able to remember what has happened before, and therefore, it becomes a handy tool for us to model the time series. So, the correlogram gives an important information about the process. So, whenever we are dealing with time series analysis, we first plot the time series as observed, and then the next step is to compute the correlations rho k for various lags k and plot the correlogram. Correlogram immediately gives us important information about the time series, which we will see through some examples. Having defined the autocovariance and the autocorrelation, we define the autocovariance for k, that is gamma k, and autocorrelation rho k. We now formulate the two important matrices, the autocovariance matrix and the autocorrelation matrix by varying k. So, we talk about the autocovariance matrix for various values of k. Similarly, autocorrelation matrix for various values of k. We form the autocovariance matrix by writing x 1, x 2, etcetera x n. These are the n random variables across n time steps, and here again x 1, x 2, etcetera x n along the rows. So, we write the elements of this matrix as consisting of the covariance between x 1 and x 1, which is gamma naught, x 1 and x 2, which is gamma 1, x 1 and x 3, which is gamma 2, and so on, x 1 and x n, which will be gamma n minus 1, going by the definition here. So, we are writing x 1 and x 1, x 1 and x 2, which becomes 1 plus 1. So, k becomes 1 there, and therefore, this becomes gamma 1, x 1 and x 3, k becomes 2 there, and this becomes gamma 2, and so on. So, this is how we write the first row. Similarly, second row x 2 and x 1, which is the same as x 1 and x 2, which is gamma 1, x 2 and x 2, which is gamma naught, and so on, gamma n minus 2. Like this, we write for the nth row x n and x 1, which is the same as x 1, x n and x 1, which is gamma n minus 1, and so on. We write the last row. This is a n by n matrix. This is the symmetric matrix. It is symmetric about the diagonal, and it is also a positive definite matrix. It can be shown that the autocovariance matrix is also a positive definite matrix. What is a positive definite matrix? One definition of the definition of positive definite matrix is that all the eigenvalues of the matrix are positive, then it is called as a strictly positive definite matrix. Now, we will divide this by gamma naught. What is gamma naught? Gamma naught is simply the variance. So, we will divide all the elements by gamma naught, then we will get the auto correlation matrix. Remember here auto correlation is simply gamma k by gamma naught. So, all the elements of gamma k we simply divide it by gamma naught, we get the auto correlation matrix. So, the auto covariance matrix is denoted by tau n or gamma n, I am sorry, this is gamma n. The auto correlation matrix is denoted by P n. So, P n is simply gamma n by gamma naught. So, the first element gamma naught by gamma naught, that becomes 1, gamma 1 by gamma naught becomes rho 1, gamma 2 by gamma 1 gamma naught becomes rho 2, and so on. So, this is how we get the correlation matrix, auto correlation matrix 1 rho 1 rho 2 etcetera rho n minus 1. So, like this we write all the elements and formulate the auto correlation matrix. The auto correlation matrix P n is also symmetrical, and it is also a positive definite matrix. Now, the fact that the auto correlation matrix is a positive definite matrix comes in handy. A positive definite matrix has the property that the fact that all the eigenvalues are positive, it also implies that the minors of the matrix are all positive. So, 1 by 1, the minor of 1 by 1 is 1, the minor of size 2 by 2 is 1 rho 1 rho 1 1, the determinant of that should be positive. The minor of size 3 by 3, that should be positive, determinant of that should be positive, and so on. So, if you look at the minor 2 by 2, that is 1 rho 1 rho 1 1, the determinant of that should be positive, because P n is a positive definite matrix, and that turns out to be 1 minus rho 1 square must be greater than or equal to 0, and this indicates that rho 1 has to lie between minus 1 and plus 1. We use the fact that P n is a positive definite matrix subsequently when we do time series analysis, and then generate several conditions from the fact that it is a positive definite matrix. Okay. We have the definition for gamma k, which is the covariance, auto covariance function, auto covariance, which is given by expected value of x t minus mu into x t plus k minus mu. Remember, we are talking about a series which is stationary in mean as well as variance, and therefore, we take the same mean mu here. The sample estimate for this is given by C k is equal to summation t is equal to 1 to n minus k x t minus x bar x t plus k minus x bar, and R k is given by Ck by C naught. Rk is the sample estimate for the autocorrelation at lag k. So, rho k would have been defined as rho k, which is the autocorrelation. We would have defined rho k as gamma k by gamma naught, and R k, which is the sample estimate of rho k, is simply C k by C naught. C k is the sample estimate of the autocovariance and C naught is simply our sample estimate of the variance. So, when you have sample estimates and you take discrete values of k, for example, k is equal to 1, k is equal to 2 and so on, and plot the sample estimates of rho R k versus k, the sample estimates R k and versus k, which is actually the autocorrelogram or the correlogram, you get spikes like this. For example, k is equal to 1 may have a R k value like this, or k is equal to 2 may have like this, etcetera. So, like this you get spikes, and this is the correlogram. So, the autocorrelation function or the correlogram may indicate some such fluctuations like this. So, for certain processes it may simply be decaying like this, with time it may be decaying. If it is a purely random series or purely a stochastic series, then theoretically rho k must be equal to 0, because x t and x t plus k are not related at all, and we have seen that for a purely stochastic process your covariance, autocovariance must be 0, and therefore, if you have a purely stochastic process, then rho k must be equal to 0 for all k. But R k we have estimated from a sample, R k may not be 0, although we may determine it from a purely stochastic series. The estimated values of R k may not be 0. The R k for a random series follows a normal distribution. It can be shown that it follows a normal distribution with a 0 mean and a standard deviation of 1 over root n, where n is the number of observations. We use this fact to examine whether the sample comes from a purely random series, or in fact, we use this fact to examine whether a given value of R k, which is a sample estimate of the autocorrelation at lag k, whether it is a significant autocorrelation or not. So, the R k for a random series follows a normal distribution with 0 mean and variance of 1 over root n. I am sorry, the standard deviation of 1 over root n. So, about 95% of the values lie between 1.96 over root n and minus 1.96 over root n and plus 1.96 over root n. So, if you have a R k value higher than this, above this limits, then that R k value can be considered to be statistically significant at 95% level. So, once you compute your R k values for the sequence, that is you have the observed values of the random variable, let us say stream flow at a particular location over last about 40 years or some such thing. So, 40 years of stream flows observed monthly, which means you will have 480 values, 12 into 40, 480 values. For the 480 values, you may compute the autocorrelations at several lags, maybe let us say up to about 50 lags you go. So, up to 50 lags you have computed the R k values. Then you plot the R k values, which gives R k versus k, which gives the correlogram, and then you draw the lines corresponding to the significance levels of the R k, which is this is a 95% significance level minus 1.96 by root n plus 1.96 by root n, where n is the number of observations. In the case that I just mentioned, you had 480 values. So, n becomes 480. Any autocorrelation which is beyond the significance bands that we have just drawn, that becomes a significant autocorrelation value. All other values which lie within this band are insignificant at level of 95%. So, let us take an example now. So, you will have a series of observed values. So, this is the x t which is observed. Let us take 10 values and compute the autocorrelation for k is equal to 1. The sample estimate for R k, the sample estimate for gamma k, which is R k, is given simply by C k, which is estimated like this, divided by C naught, which is the sample estimate for variance. There are various other expressions for sample estimate of rho k, that is, there are various other expressions available for R k, but we will use this particular expression simply C k by C naught. So, we compute x bar first from summing of this. So, x bar is known and then x t minus x bar. Because we are talking about k is equal to 1, which means you are getting the sample estimate for rho 1. So, we lag the series by 1 time unit. So, we write corresponding to x t, we write x t plus 1. So, x 1 associated with that, x t plus 1 will be x 2. Associated with x 2, we have x 3, which is 121. X 4 corresponds to x 3 plus 1. So, 117. Like this, we lag the series, that is, we shift the series by 1 time unit and then write the series x t plus 1. Then we take x t plus 1 minus x bar. X bar is computed based on the values of x t given here, x t plus 1 minus x bar. Then the multiplication of this x t minus x bar and x t plus 1 minus x bar, that is this summation. And from this summation we get the covariance, that is autocovariance, as we get the variance first as 459.2, and similarly we get the autocovariance at lag 1, which is C k, as 329.375. Where what did we do here? We summed up these values and then use this sum to get the autocovariance at lag 1. From the autocovariance, we get the autocorrelation, which is C 1 by C naught, that is R k will be C k by C naught and C naught is the variance. So, R 1 will be C 1 by C naught, that comes to be 0.72. I would like to indicate a small correction here. This value is negative and therefore, the C 1 that you get here will be negative. So, this is negative and the correlation R 1 will be negative. So, R 1 is minus 0.72. So, this is a negative correlation. Let us say now, if you are looking for not k is equal to 1, but k is equal to 2, what you would have done for this example? Here we are putting x t plus 1 for k is equal to 1. So, if you are interested in k is equal to 2, you will put x t plus 2, which is corresponding to t is equal to 1, you will put the value of 121 here and then 117 here, 79 here, etc. So, essentially you will lag the time series by 2 units instead of 1 unit as you did here for k is equal to 1, and k is equal to 3 similarly you will have lagged it by 3 units. So, how many values you would have to compute this? In the case of k is equal to 1 for this particular case you had 9 values, for k is equal to 2 you had 8 values, for k is equal to 3 you will have 7 values and so on. And therefore, as your lag increases you are estimating based on smaller and smaller number of values. Your values will be, your estimate will be based on smaller and smaller number of values, because as you can see here the summation is from k is t is equal to 1 to n minus k. For k is equal to 1 you will have n minus 1 values, k is equal to 2 you will have n is equal to you will have n minus 2 values and so on. And therefore, we generally estimate the row case or the autocorrelations up to about 0.25 n, where n is the number of observations. That means, up to about 25% of the number of observations you compute row k. All right. Now, we know how to compute for various values of k. In this particular case we computed for k is equal to 1. So, we also know how to do it for k is equal to 2, k is equal to 3 etcetera. You simply lag the time series by those many time units and then use the same procedure and compute associated with various values of k. We said that for a purely random series, the row case should all be insignificant. For k not equal to 0, of course, row 0 will be always equal to 1 irrespective of which series you are talking about, because you are talking about the autocorrelation of a variable with itself, and that has to be equal to 1. But for other values of k, that is k other than 0, k not equal to 0, your row case should all be insignificant, statistically insignificant, if it is a purely random series. Let us examine this now. Let us generate 40 uniformly distributed random numbers, that is 2 digit random numbers, and see what happens to the autocorrelations. We will compute autocorrelations up to let us say lag 10 or something. So, this is the data, these are the number serial numbers, and this is the data on uniformly distributed random numbers 98, 69 etcetera. So, then 11, 12, 13, 20. So, this is the data. So, you have 40 values of uniformly distributed random numbers between 0 and 100, 0 and 99 in this particular case. We will compute the autocorrelations up to lag 10. When we do that, you get values like this: k is equal to 0 is 1, k is equal to 1 is 0.0235, k is equal to 2 is minus 0.183 etcetera. And when you plot this, the plot will be something like this. It appears to be like this. Now, your n is 40, because you had 40 data, n is 40. So, 1.96 by root 40 is 0.31. So, you draw a line minus 0.31 and plus 0.31 and see that, ensure that all the values that you have got for row k are in fact lying within this band minus 1.96 to plus 1.96. Now, this happened in this particular case because they were all random numbers, uniformly distributed random numbers, and therefore, there is no dependence of one number on any other number in the series, and therefore, your autocorrelations at all lags that we considered are all zeros, are all insignificant, which means the hypothesis is that the RK that you thus obtained have a mean of 0. This 1.96 by root n, normally for convenience you take it as 2 by root n. So, simply remember 2 by root n. So, whenever you compute the RKs, you compare those RKs with 2 by root n, and if it is more than plus or minus 2 by root n on either side, then it can be considered significant. Now, the significance of RK is important because we are looking at the dependence, whether a particular value at a time t depends on another time the value at another time t minus k, that is given by rho k or r k in this case. In the case of samples we denote it by r k, and given a value of r k we should be able to say whether it is significant or not. Often we make a mistake that let us say we compute a correlation of 0.7 and say that 0.7 is a very high value and therefore, there is a significant dependence. Remember that the significance of the autocorrelation or any correlation depends on the sample size. So, if your sample size is high, let us say instead of 40 we had 400 values, then what would have happened? This value would have been much smaller. So, as the sample size becomes larger and larger, the significance level of the correlations becomes smaller and smaller. For example, we may have a correlation as small as 0.2 being significant if the sample size is large, and a correlation as high as 0.6 may be insignificant if the sample size is very small. So, remember always that the significance of the correlation depends on the sample size. As we just saw, if we have a purely stochastic process, then all the correlations apart from at lag 0 lag equal to 0, all the correlations must be statistically insignificant. So, if you have a sequence of observed flows and you compute the rho k's or you estimate the r k's and then observe that all the r k's are statistically are lying within this band, then they are all statistically insignificant and therefore, it indicates a purely stochastic process. Now, this has an important connotation when we start looking at data generation and so on. If you have a periodic process, let us say you are looking at monthly stream flows in a monsoon climate like ours, and you have 480 values as I just mentioned, 40 years of monthly stream flow data. So, 480 values, you compute the lags, you compute the R k and then plot the correlogram, then you may get the rho k something similar to this. So, it is periodic in nature. So, the periodicity of the process comes up when we plot the correlogram, and this gives an important indication of the important information about the process itself. That is, if you have the data on monthly time series and compute R k and then plot the correlogram, if the correlogram indicates that there is a periodicity, if the correlogram is periodic in nature, it indicates that the time series has a periodicity inherent in it. So, what do we do with all this information now? We have plotted the time series. Let us say we have observations for last so many years on observed stream flows at a particular location or observed rainfall at a particular station. We have collected all these values and plotted the time series. Then we also know how to compute the correlations, autocorrelations and autocovariance. We know how to formulate the autocovariance matrix and so on. The whole purpose of the time series analysis is to extract information about the observations that we have made and then use this extracted information for decision making purposes. Let us say that we want to build a reservoir, build a dam at a particular location, and you have made the observations on the last 50 years of stream flows. You have the information on the last 50 years available with you. We must extract the information content in the observations and use that information content to make decisions about the future. Now, these decisions may be long term decisions. For example, any hydrologic design that you want to make on a physical structure. Let us say you want to make a bridge pier or the height of the bridge, etcetera, you want to decide based on the flood levels. Now, this is actually a long term decision that you are making based on the historical data that is available. That means, you are making a decision which has implications for a long period of time in future. Similarly, you want to design a dam, the height of the dam or the capacity of the dam, etcetera. You are basing these decisions on the historical available data, and this decision has a long term implication in terms of its serviceability. Let us say it has 100 years of serviceability. So, you are making the decision based on the last so many years of data, let us say 30 years of data or 50 years of data, and then the decision that you are making has a implication over a long period or in future. That is, we are talking about long term decisions. It may be either data generation, data extension, etcetera. So, you use these techniques to make long term decisions. On the other hand, you may be interested not so much in the long term, but in the immediate short term. Let us say you are standing at June of 2010, and then you would like to examine what is likely to happen to the flow in July of 2010, that is the immediate next month. So, you would be interested in forecasting what is likely to happen in the near future or in the immediate next time period or next 2 time periods, next 3 time periods, next 1 season and so on. So, you will be interested essentially in the short term implications. So, these techniques that we are now introducing will have applications on both long term as well as short term. When we are talking about long term, we call it as either data generation and data extension, or when we are talking about short term, we will be interested in data forecasting. Now, the data forecasting applications are many in hydrology. We may be interested in flood forecasting. There is a rainfall that is occurring in the catchment and you would like to forecast the floods at a particular location, or a flood peak is known to have started along the river and then you would like to forecast the flood movement across time in the same river. So, that is called as forecasting problem, whereas extension and data generation problems are essentially planning problems, where you look at long term implications of the analysis of the observations that we have said we have with us to make the decisions. So, in both these, whether it is a long term decision making or for short term applications through forecasting, we use the historical data, and the premise there is that the history provides a valuable clue to the future, because we do not have any other means of making judgments about how the future is likely to be. We use the historical data, historical time series, and then make judgments about how the future is likely to be. That is the whole concept of time series analysis, and especially the stationary time series analysis that we have been dealing with. In the stationary time series analysis, what are we saying? That the properties remain the same across time. So, x t and x t plus 1 have the same probabilistic properties, and we assess these probabilistic properties based on the historical data that we have, and then use the same probabilistic properties for the future and make our judgments and make our decisions. So, we will summarize today's class, today's lecture. Essentially what we did today was to introduce the concepts of time series. We went through the definition of time series again and saw what we mean by a realization and an ensemble. We saw what we mean by time properties, time average properties and ensemble average properties, where we are talking about the properties across realizations at a given time. We also briefly defined what we mean by an ergodic process. If your time average properties across time for a realization are the same as ensemble average properties, then the process is called as an ergodic process. Then we introduced autocovariance, the definition of autocovariance, and then autocorrelation and the sample estimates, how we estimate the autocovariance and autocorrelation from the sample estimate from the samples. The autocorrelation at lag k, denoted by rho k, it is estimated by R k, which is a sample estimate. The plot between rho k and k, or when you are dealing with samples R k and k, is called as the correlogram or the autocorrelation function. Now, the correlogram gives an important information, about the time series. For example, if it is a purely stochastic time series, then all your rho k's for k not equal to 0 will all be insignificant. What do we mean by insignificance? That they lie in the band 2 by root n approximately, or 1.96 by root n precisely at 95% significance level. So, if all your RKs lie within that band, then they are all statistically insignificant. If you have a sample value, if you have observed values and then compute the rho k's and they are all statistically insignificant, it indicates that the sample is drawn from a purely random process, which we will use. This fact we will use in data generation. Then we also saw, if you have a periodic process, then the rho k or the correlogram will be oscillating periodically. So, if you have a sample and then you compute the period rho k, plot the correlogram, and if you see the correlogram is oscillating periodically, then it gives you an indication that your sequence is periodic, and we use this fact in our further modeling. So, we will continue this discussion in the next lecture, where we will be dealing with data generation as well as data forecasting techniques. Thank you for your attention.